Hello friends, let us now learn some important points about attenuation coefficient. Attenuation coefficient is a measure of quantity of radiation attenuated by a given thickness of absorber. The name of the coefficient is determined by the units used to measure the thickness of the absorber. Four attenuation coefficients are described in classic texts of radiation physics, but here we discuss only two important types of attenuation factors. One, linear attenuation coefficient. Second, mass attenuation coefficient. The important coefficient in uh, most important coefficient for diagnostic radiology is linear attenuation coefficient. Linear attenuation coefficient is a quantitative measure of attenuation per centimeter of absorber. So it tells us how much attenuation we can expect from a certain thickness of tissue, because so we measure the patient thickness in centimeter. So how much attenuation is done for for a certain thickness of tissue is linear attenuation coefficient. It is a practical and useful attenuation coefficient. The linear attenuation coefficient is given by the units 1 per centimeter, and thus the name linear attenuation coefficient because centimeter is a linear measurement. The expression per centimeter is same as 1 by centimeter or centimeter inverse. Linear attenuation coefficient, it is important to realize that the linear attenuation coefficient is mainly for monochromatic radiation, and it is specific for energy of the X-ray beam and the type of absorber. Water, fat, bone and air all have different linear attenuation coefficient, and the size of the coefficient changes as the energy of the radiation changes. If the energy of radiation increases, the number of X-rays attenuated decreases. So the linear attenuation coefficient also decreases. There are some mathematics involved in this linear attenuation coefficient. The formula is n is equal to n naught exponential to the power of minus mu x, where n is the number of transmitted photons, n naught is the number of incident photons, and attenuated photons is equal to the transmitted photons minus, incident photons minus transmitted photons gives attenuated photons. So attenuated photons is equal to the number of incident photons minus number of transmitted photons, n naught minus n, and mu is the linear attenuation coefficient and x is the absorber coefficient. This is similar to the radionuclide decay, but we are not going to discuss that more. The next important thing in linear attenuation coefficient is half value layer. Half value layer is the thickness of the absorber required to reduce the intensity of original beam by half. This is a common method for expressing the quality of the X-ray beam. So the formula is n is equal to n naught exponential to the power of minus mu x. So n by 2, because it is required to decrease the intensity of original beam by half. So intensity is decreased by half. So n naught by 2 is equal, original incident beam is n naught. So the transmitted beam is reduced is equal to the intensity of incident beam by 2 is equal to n naught exponential to the power of minus mu x. So after calculation, mu x is equal to 0.693. So half value layer is equal to 0.693 by mu. So attenuation of monochromatic radiation um, is given as mu here, and the half value layer is equal to 0.693 by mu. So half value layer is inversely proportional to the linear attenuation coefficient. So it is a common method of expressing the quality of the beam. A beam of high half value layer is more penetrating than the beam with low half value layer, because if the beam has higher half value layer, the it penetrates for a longer. So half value layer is this thickness of penetration, thickness of absorption. thickness of absorber required to decrease the intensity of original beam by half. So more the thickness of absorber penetrated by the beam, so more is the penetrating quality of the beam. So high half value layer shows more penetrating quality than the lower half value layer. So there are some tables which are given with the list of linear attenuation coefficients for substances like water, sodium, bone, sodium iodide and most of the elements. With linear coefficient attenuation coefficients, from these tables we can calculate the percentage of transmitted photons for the whole variety of photon range and for whatsoever or whatever thickness of tissue we may choose. So the next important coefficient is mass attenuation coefficient. The other useful attenuation coefficient in physics literature is mass attenuation coefficient. Mass attenuation coefficient is used to quantitate the attenuation of materials independent of their physical state. For example, water, ice, water vapor are the three physical states of water. All of them have different linear attenuation coefficient, but they have same mass attenuation coefficient. It is obtained, mass attenuation coefficient is obtained by dividing the linear attenuation coefficient with density and has a symbol mu by rho. The units of mass attenuation coefficient is per gram per centimeter square or 1 by gram per centimeter square or centimeter square per gram. There are two important things which you have to see in the units. One, linear attenuation coefficient and mass attenuation coefficient. So first, units of absorber in mass attenuation coefficient and linear attenuation coefficient. Units of absorber. Absorber is how much thickness is absorbed. For linear attenuation coefficient, units of absorber is centimeter, whereas units of X-ray absorber in mass attenuation coefficient is gram per centimeter square, which contains mass unit. Whereas units of linear attenuation coefficient is inverse of the absorber in linear attenuation coefficient, that is 1 by centimeter. Similarly, units of mass attenuation coefficient is inverse of this mass attenuation absorber in mass attenuation coefficient. So this is false. This is actually centimeter square per gram or 1 by gram per centimeter square. So this is a little mistake. Okay, you should see this one is little mistake. So if you take thickness of 1 gram per centimeter, water has 1 centimeter volume, whereas ice has 1.09 centimeters of volume. Water vapor has 1670 centimeters of volume. This is a simple way to understand linear and mass attenuation coefficient. So if you see, so 1 gram per centimeter square and centimeter is equal to this. So all water, ice and water vapor vary in density, with water having highest density and water vapor having lowest density. So if you see the linear attenuation coefficient of water and linear attenuation coefficient and mass attenuation coefficient, for water both linear and mass attenuation coefficient is same, whereas for ice the linear attenuation coefficient is 0.196, which is less than that of water, whereas water vapor has even more lesser linear attenuation coefficient, that is 0.00128, whereas mass attenuation coefficient for all of them is constant. So 1 centimeter volume of water. So if you see the linear attenuation coefficient of water is 0.214 and 1 centimeter thickness. 1 centimeter thickness of water will absorb 20% of the incident beam. Whereas the same thickness of ice, if you take the same thickness of ice, some 1 centimeter thickness of ice will absorb 18.5% of beam, because ice is a little lesser dense than that of water, whereas water vapor is very little density and thus the water vapor will absorb nothing in 1 centimeter thickness. So 1 centimeter thickness of water will absorb 20% of beam, 1 centimeter thickness of ice will absorb 18.5% beam, whereas water vapor, 1 centimeter of water vapor will absorb nothing. So density has a profound effect on the X-ray attenuation at all levels. If you see the mass attenuation coefficient for all these is 0.214 centimeter square per gram, which is same as the linear attenuation coefficient. They must be same because the density of water is 1 gram per centimeter cube, which is same for all of these, and the mass attenuation mass attenuation coefficient is equal to linear attenuation coefficient by density. Density of all these will differ, and thus because we are cancelling the density or independent of the density, mass attenuation coefficient will be same for all the for water, ice and water vapor, because it is logical that 1 gram of water, ice and water vapor has exactly the same amount of mass. Thickness of 1 gram of per centimeter square of water, thickness of 1 gram per centimeter square of water is 1 centimeter, whereas thickness of 1 gram per centimeter of ice is 1.09 centimeters, and thickness of 1 gram per centimeter square of water vapor is 101. Thickness of 1 gram per centimeter square of water vapor is 1670 centimeters. These thicknesses will attenuate the same amount, that is 20% of energy, because all of them contain the same amount of mass. Thus, mass attenuation coefficient is independent of density, whereas coefficients of water, ice and water vapor, mass attenuation coefficient of water, ice and water vapor are all same, but their densities will vary considerably. To say that 1 gram of water and 1 gram of water vapor both absorb the same amount of radiation is true, but it has no diagnostic meaning. It is misleading because we do not deal with gram per centimeter square in the patients. What do we generally deal in the patients? We deal with centimeters in the patient, that is thickness of the patient, but not the gram per centimeter square. Patient thickness is given in centimeters, and 1 centimeter of water absorbs a great deal of X-rays than 1 centimeter of water vapor. So, linear attenuation coefficient is very important, whereas mass attenuation coefficient, where the effect of density is removed, is more misleading. So, these are the important points about the linear and mass attenuation coefficient. Thank you.